This meeting is being recorded.
So today we are going to see two variable generating functions first, and then we'll go to, so that will finish our preliminaries for the moment. Okay? So let's start with the idea of two variable generating functions for normal integer partitions. So if you recall, we had this one variable generating function where, uh, the variable was q, which kept track of the number of which we are looking at the partition of, right? So this was given by this infinite product, and we had this very shorthand notation to write such infinite products. Okay, so this was our one variable generating function for normal partitions, and we also saw the one variable generating function for partitions into distinct parts. So if dn denotes the number of partitions of n into distinct parts, then the one variable generating function for dn was something like this. Right? And we can write this as minus q comma q infinity in the shorthand notation. Okay. So these are the two generating functions that we want to extend into a two variable generating function. So in the two variable case, we want to keep track of, okay, so let me also mention another way of writing this. So if you think about this, this generating function is actually also equal to something like this. So q raised to the power the norm of lambda, where lambda is any partition. Okay. So the norm of lambda is just the sum of all the lambda i's. Okay. And in particular, if lambda is so this sum runs from I equal to 1 to the length of lambda. And in particular, if lambda is a partition of n, then q raised to the power norm of lambda is going to be q raised to the power n only. Okay, so this is, so if you think about it, this equality, this equality is also another way of representing the generating function for partitions. Okay, now similarly we can also write this as something like, say, lambda is coming from, let's write d of dp, which is, say, the set of all distinct partitions. Okay, q raised to the power the norm of lambda. All right, now we want to generalize this generating function into a two variable generating function, where we want to also keep track of the number of parts that appear in each partition. Okay, so basically what we want is this generating function. So let's say z is the variable which is keeping track of the number of parts in some partition. So the number of parts in a partition is just the length of that partition, right? So yeah, so z is keeping track of the length of that partition, and q is keeping track of the number of which lambda is a partition of. Okay, so we are interested in this two variable generating function. Okay, and if you want to write it in this notation, then this is just going to be equal to let's say so n going from 0 to infinity, but now we also keep track of the parts, so the part size can start from, say, 0 and it can go on, and let's say pln, this denotes the number of partitions of n into L parts. And this will be z raised to the power L and q raised to the power n. Okay, so this is the analog. This generating function is the analog of this generating function, where we introduce the new variable z to keep track of the number of parts in the partition as well. Okay, and it would be nice if we can, for this generating function, if we have some nice product formula of this type. And if you think about this a little bit, you'll see that actually we have already seen what that product formula should be. And this is equal to, I'll write this down and I'll explain why this holds. So this is nothing but 1 over zqn, where n goes from 1 to infinity. Okay, and if you set, if z goes to 1, then we get back the generating function for partitions. And this is what it should be, right? So if in this case, if in this quantity you set z equal to 1, or in this quantity you set z equal to 1, you should get back this previous quantity, and this quantity, correct? So why is this generating function true? And if you think about the proof of the one variable generating function for partitions, the proof should immediately tell you why this generating function is true. So remember, we looked at something like we looked at the first two factors initially, okay, and this was sort of giving us something like 1 plus q raised to the power 1 plus q raised to the power 2 plus q raised to the power 1 plus 1 plus q raised to the power 2 plus 1 plus q raised to the power 1 plus 1 plus 1, and so on. Okay, so basically these two factors were generating the partitions where the parts are coming from 1 and 2 only. And if you multiply the third factor, which is 1 over 1 minus q to the 3, then you will get partitions which come whose parts come from 1, 2, or 3. Okay, so if you think about this, what happens if you sort of multiply a z with each of the powers of q? Okay, so let's look at what happens here. So we have 1 over 1 minus zq times 1 over 1 minus zq squared. So these two are the first two factors of this generating function, two variable generating function. And in this case, what you will see is it will be exactly the same thing as what we had here, but this time we'll have a z multiplied with each term where a q appears. Okay, so you'll get z q to the 1, and this will be z q square, but this will be z square q 1 plus 1, and z square q 2 plus 1, and z cube q 1 plus 1 plus 1, and so on. So why is this the case? So if you think about how this q to the 1 is coming, this is coming when you multiply 1 with q to the 1. Okay, but in this case you have a z multiplied with the q, so you will get a 1z here. Okay, similarly q square is coming when you are multiplying the 1 with q square, and there is a z in front of the q square, so you get a 1z here. Okay, a factor of 1z here. Similarly, this q raised to the power 1 plus 1 is coming when you multiply q plus q times q. Okay, so that means you're multiplying two q's, and with each q there is a z, so you get a z square here. Okay, and similarly here you get this when you multiply q and q square, and there is two z's associated with the q's, so you get a z square. Similarly, z cube, and so on. Okay, so now this is just the same thing as extend this argument like we did for the generating function. Pn, and we should get a proof of this quantity here. Okay, so this is the two variable generating function for partitions, where one variable is keeping track of the length of the partition, that means the number of parts in the partition, and another variable is keeping track of the norm of the partition, that means of which integer that partition is. Okay, now from here it should be clear what the two variable generating function for the distinct parts partition is. Okay, so if you think about this, if you look at the distinct parts partition, so what we want is the following. So we want z raised to the power l, q raised to the power norm of lambda again, sorry, l of lambda, q raised to the power norm of lambda again, but this time the lambda is coming from the distinct parts partition. Okay, and this is equal to, so you can write this again as a double sum. So this will be n going from 0 to infinity, l going from 0 to infinity, and let's write q and l, where this is now the number of partitions of n into distinct parts, sorry, into l distinct parts. Okay, z raised to the l, q raised to the n. So this is our two variable generating function, and immediately it should be clear that the two variable generating function for this case is nothing but 1 plus z q to the I I going from 1 to infinity. Okay? And again, if you set z equal to 1, then you get the generating function for d of n, which is the partitions into distinct parts. Okay? So that's the idea of two variable generating functions. We can actually get many different nice results for the two variable generating function case. And let me mention two results. One is by Euler and one is by Cauchy. Let me first do Cauchy's result. So I'm going to write it down, and I'll explain how one side of the picture comes. Okay. So again, this is a sum equal to product identity. All right. So this is Cauchy's result. I think it must have also been observed by Euler. I don't know. So n going from 0 to infinity, z raised to the n, q raised to the n square plus n divided by qqn, zqqn is equal to 1 over zq infinity. Okay. So this is Cauchy's result. And if you look at this quantity, then this should be clear that it is the two variable generating function for partitions that we just saw. Okay. 1 over zqqq infinity is the two variable generating function. So if you write it in product notation, this is nothing but this product, right? So 1 minus zq I, let's say, and I is going from 1 to infinity. Okay. Right. Yes. So I is going from 1 to infinity. So this was the two variable generating function for integer partitions that you just saw. So that means the z that appears on the left hand side must be keeping track of the number of parts in the partition, right? So this n, which is the summand, has to be keeping track of the number of parts in the partition. But what about q n square plus n? This looks quite different. Okay, so let's try to parse this combinatorially right now. Okay, so this brings us very nicely to the idea of Durfee squares. So if you think about any partition, uh, it's always possible to form a largest square which is lying inside the Ferrer's diagram of that partition. So if you think about a Ferrer's diagram of the partition, how does it look like? So let me pick a random. So I'll pick 3 random partitions. Random, I mean, I don't know, however random you can. Okay. And then the third partition is just this single dot. Okay. So this is one partition. This is one partition. This is another partition. And the third one is just this, or we can, extend it to a single. Actually, we can also pick some. Okay. So these are 4 partitions. So this partition, the first partition that I have drawn to the extreme left, is a partition of 5, which is just 1 plus 1 plus 1 plus 1 plus 1. Similarly, the second partition that I have drawn is a partition of 6, which is just which has just a single part, which is 6. Okay, and this is now going to be a partition of 5 plus 3 plus 3 plus 1 plus 1 plus 1. Okay, and the final partition will be 5 plus 3 plus 2 plus 1. Okay, so now observe that in each of these partition, if you take the largest possible square that you can draw, starting from the top left dot. Okay, what I'm saying is this. So you start from this particular dot and you try to extend the square. So if you draw just just a square covering this dot, then this is just a 1 into 1 square. But we'd like to extend it, okay? So that the whole of the square lies inside the diagram. So we can extend it to a 2 cross 2 square here, such that all of the 4 dots inside that square is lying in the diagram. But if we try to do it for a 3 cross 3 dot, then we see that there is 1 dot which is missing from this diagram. So basically the corner, the bottom right corner dot is missing. Okay, so this 3 by 3 square is not possible to be drawn. But the largest square that we can draw in this way is basically this square. Okay? And we do the same thing here. So in the other case, so we see very easily that 1 cross 1 square is possible. Then 2 cross 2 square is also possible. And then finally, we see that the 3 cross 3 square is also possible in this case. But if I try to do a 4 cross 4 square, then I see that there are several dots which are missing. Okay. So that means in this case, the largest square which is possible is this 3 cross 3 square. For the other cases, it's pretty simple. We see that 1 cross 1 square is possible, but as soon as we go for 2 cross 2, we see squares missing. Similarly, here 1 cross 1 is possible, but as soon as we go for 2 cross 2, we see that the squares are missing. So in both these cases, we can draw a 1 cross 1 square. So these squares that I have drawn, the maximal square that we can draw such that all the dots in the Ferris diagram are enclosed by the square. These squares are called Durfee squares. Okay. So these are called Durfee squares. All right. And if you look at, so if you think about the generating function of partitions, so suppose this, let's say this partition, okay, which is a partition of 11. So in the generating function for for all partitions of 11, there is this q raised to the power 5 plus 3 plus 2 plus 1 term which is appearing, okay? And this particular q raised to the power 5 plus 3 plus 2 plus 1 term which is appearing is coming from this partition. So each dot is giving us one factor of q, okay? And the total number of dots is basically giving us the exponent of q, which is appearing in the generating function for partitions, right? So with that idea, let's try to see what the left-hand side of this sum identity is, okay? Or sorry, of this Cauchy's identity is. You see the bottom part. So there are two q factors here, okay? Q programmer factors here. So one factor, which is 1 over QQN, this is pretty easy to understand combinatorially. So if you think about this, we have seen this already. So 1 over QQN, this is nothing but the generating function for partitions into at most n parts. Okay. So 1 over QQN is the generating function for partitions into at most n parts. And the other factor, which is 1 over ZQQN, which is this second factor here appearing in the sum side, this is going to be the generating function for, again, partitions into at most n parts, but this time the z is keeping track of the number of parts. Okay, so this z is keeping track of the number of parts which appear in that partition. Here there is no z, so we don't need to keep track of the number of parts that appear. And if you think about this, so q n square, if the largest Durfee square that you can draw in the Ferris diagram of a partition is of side length n, then the number of dots which are enclosed by the Durfee square is n square. Okay? So side length n square, n, and you just multiply n into n, you get n square, which is the number of dots which are enclosed. So basically, this q raised to the power n square is keeping track of the largest Durfee square that is appearing. It's just saying that the largest Durfee square is of side length n. Now, what about the extra n which is appearing here? For that, let's look at say this partition. Okay, so this partition, let's look at this partition. So once you take away the Durfee square, which is basically the blue colored thing that you see here, there still remains certain dots. Okay, so I'm going to draw this in green. So you have this green part and you have this yellow part in the bottom. Now, if you think about these two pieces which are remaining, so if in this case, the length of the Durfee square is 2, okay? So the blue square is of side length 2. And if you look at the green part which is there, you see that that is a partition. So it's a partition, but the cap is that the number of parts in the partition has to be at most 2, which is basically the size of the Durfee square. So in this case, the partition is 3 plus 1. And the bottom part in yellow that you see is also another partition. But again, in this case, the partition is, so it's bounded, the largest part of the partition is bounded by the Durfee square. It cannot exceed the Durfee square, okay? So if it exceeded the Durfee square, then the Durfee square would have been bigger. So apologies, so I think the slide has gone missing, but let me share it once again. So I'm trying to go slow because I don't know if everyone has seen combinatorial proofs of this type. Right. So, okay. So what we're saying, let me go through it once again. So if you think about this, let me draw a better picture. Okay. So if you think about this, you have a Durfee square, which is enclosed by this blue square, and then you have a partition which is adjoining the Durfee square, and you have another partition which is below the Durfee square. Okay, so these are the three pieces that I have shown you. Now, if you think about this is going to be a partition where number of parts is less than equal to n if the side length of the Durfee square is n. Okay, so the number of parts is going to be less than equal to n. And in this case, this is going to be a partition where the largest part is less than equal to n. Okay, so but if we remember the conjugation operation that we saw in the first lecture, then both of these partitions are actually the same class of the same class. You just flip the picture, okay? So what I'm saying is this. So this yellow thing, if you sort of flip it and say do the conjugation, then sorry, I should have. Then you get back the orange part. Okay, so this is what I'm saying, and you can go back and forth. All right. So both of these partitions are the same thing, and that's basically what is appearing here. Okay. So in one of these, so I'm going to explain it, and I don't know if it is still clear or not. So this 1 over QQN, you can think of it as coming from this yellow part, where we are not keeping track of the number of parts, okay? And the ZQQ infinity is coming from this green part, where we're keeping track of the number of parts. So basically this whole thing we're keeping track of. And we know that the side length of the Durfee square is of length n. So there will be a z to the n factor here, okay? So this is the z to the n factor. This is q raised to the n square. And q raised to the n is just coming saying that we have a side length of this, sorry, we have a part which is covering, we have a partition which is covering all the dots in the first column, okay? So basically this is the explanation. Now, if you think about that, if you take the sum of all such n going from 0, 1, 2, and so on, so n going from 0 is just generating all partitions where the Durfee square is of length 0. N equal to 1 is generating all partitions where the Durfee square is of side length 1, and so on. So if you club all of these together, if you take the sum of these together, then you are basically generating all partitions. So which is what is here on the right hand side. So this is an identity of Cauchy. I have just given a combinatorial proof of this. So if you want, you can think of an analytic proof of this as well. Okay. Let me do two similar identities. Okay. So these will be now identities by Euler. So let's see. Euler's identity, and I'll write this down and I'll explain. So the explanation is sort of similar, but in this case, we are dealing with distinct parts partition. Because of that, there is a subtle thing we need to keep in mind. Okay? Sorry, there should be a ZQ. Okay. So again, if you go back to the beginning of today's lecture, you'll see that this is the two variable generating function for partitions into distinct parts, where Z is keeping track of the number of parts and Q is just keeping track of the number of which it is a partition. Okay. So in the left hand side, whatever is here should also be the generating function for partitions into distinct parts, because the right hand side is the generating function. So whatever is in the left hand side should also be the generating function. So how to understand that? And you see that this z to the n is keeping track of the number of parts. So basically what it is saying is that you have n distinct parts in the partition. Now, if you think about distinct parts, then so the lowest possible distinct part which can appear is 1. And if there are n distinct parts, then you could have, all of these uh, distinct parts appearing in the partition. Okay, 1, 2, 3 up to n. Some of them may be missing. If say 3 is missing, then you would need some other part which will appear. Okay, or say somewhere 17 is missing, then there will be another part which is appearing. Okay, so some of these things can be missing. But if there is something missing, then the part which is appearing has to be bigger than that missing part. Okay, right? So in each of these n first n positive numbers, if some part is missing in the distinct parts partition, then the missing part has to be greater than one of these 1, 2, 3 up to n. Correct? So that means whatever you do, you will always get a factor of q raised to the power 1 plus 2 plus 3 up to n. Okay. So, and if you remember your arithmetic progression, then this is nothing but n into n minus 1 by 2. Okay. So that's it basically. Basically this is coming from here. And what about the 1 over q(n)? So again, this is just the generating function for partitions into at most n parts. So if you take away all of these q raised to the 1 plus 2 plus 3 and so on, whatever is remaining is actually going to be a generating function for partition into at most n parts. So I can show you with a picture, and there is a nice picture that you can see here. So if you see this partition, this is a partition into distinct parts, 5, 3, 2, 1. Okay. And what I'm saying is the following. So what I do is I take away 1 dot here, 2 dots here, 3 dots here, and 4 dots here. Okay. So whatever is remaining, so in this case, the remaining thing is just this 1 dot. Okay. So whatever is remaining is actually a partition without, any condition on distinct parts, where the number of parts is at most the length of the previous partition. So basically, the number of parts is at most 4 in this case. Okay. We can look at a different example as well, so that this is clearer. So let's say I pick a longer one, whatever this is. Okay. So let's say this is a distinct parts partition. Clearly, it's distinct parts. So I take away 1 dot from the bottommost part, 2 dots from the next part, 3 dots from the previous part, and so on. Okay. So the final thing that I take away are 5 dots. Now, if you write down whatever is remaining as a partition again, so 4 dots remain here and 1 dot each remain in the next 3 parts. So clearly this is not a distinct parts partition, right? Because you have 4 plus 1 plus 1 plus 1. Okay. So you don't have a distinct parts partition, but you have a partition. And the only condition in that partition is that the number of parts cannot exceed the number of parts here, because there is no dot which is appearing below this red process. Okay. So the only condition on this is that the number of parts has to be at most the number of parts of the distinct parts partition that we started out with. And in this case, the number of parts was n. So whatever is remaining would be 1 over QQn. Okay. So that's again a combinatorial proof of this. So, I mean, if you are not very used to combinatorial proofs of this type, then whatever I said probably is a bit fast. So I would encourage you to, go back and think about this, whatever is happening here. Okay. So let me write down two. Actually, I'll write down three different results, and I'll not prove this result. Okay. But the third one, I'll give you a hint of how to prove it, because that's an important result. So the next two things would be some, restricted genetic function of whatever we discussed before. Okay. So let's say PDJ of n be equal to the number of partitions of n into distinct parts where the number of parts is at most j. Okay. And let me also write down, say, q of njl be now the number of partitions of n into exactly j parts, so all distinct, and no greater than L. Okay, so these are two quantities, and we want the generating function for this. Okay, and I'm going to, so this will be an exercise for you to prove, and it's very easy to prove using the combinatorial techniques that I have just mentioned. Okay, so the first would be the generating function for Pdj of n. This is a single variable generating function, and I'm saying that this is equal to q raised to the j times j plus 1 by 2 divided by qq sub j. Okay? And the second is going to be a two variable generating function. So m is going from 0 to, so L into L plus 1 by 2. 0 to L, Q, M, J, L, so it will be J, Q to be N, and this is nothing but L. Okay. So, I mean, if you have understood whatever I mentioned in the previous two results, then you should immediately see why these two things are true. Okay. But you can go back and look at the arguments and come up with a proof of this. Okay. I think these are mentioned as exercises in the book. Actually, all of the four results that I did are mentioned as exercises in the book. But let me do the final uh, two variable generating function. So this is actually a result by Sylvester, who gave a combinatorial proof of this. Okay, and it was one of the first identities of this type where you had a combinatorial proof, and then the analytic proof came out later. So this is again a generating function for two variable generating function for distinct parts partition. Okay, so minus z to infinity. This is the two variable generating function for distinct parts partition. But this time the sum side is very involved. Okay, compared to what we saw in the previous slides. So let's say j going from 0 to infinity, z raised to the power j, q raised to the power j 3j minus 1 by 2 times minus zq j minus 1 q j, but there is one factor which is remaining. Okay, so it looks very involved. So in this case, the combinatorial proof is slightly more involved. Okay, so if you think about how the distinct parts partition would look like, so in that case, you would have a Durfee square, which is say this blue square. Then you will also have some triangular shape, which is called the Franklin's triangle. Okay? So you might have a triangular shape. I think you need to work with only one of these triangles, but this triangular shape is called Franklin's triangle, and you need to keep track of what is happening in the triangle and what can appear outside the triangle. Okay? So that's a hint for the combinatorial proof. But there is a simple analytic proof, and the analytic proof is easy to say. So if you denote the sum side by f of z, then you can actually write f of z as 1 plus zq times f of zq. Okay? And once you see this, so if you can see that we can write the sum side as 1 plus zq times f of zq, then you just iterate it, right? So the next iteration would be 1 plus zq times 1 plus z square q square, and sorry, this would be 1 plus zq square and f of zq square, okay, and so on. So if you iterate this, eventually we're going to get back minus zq q infinity. Okay, so it's easy to see that this is true. One trick that we can use is to break this part, which is 1 plus zq 2j. So you can write this as, let me write it in red. Okay, so this part you can write it as 1 minus q to the j plus q to the j times 1 plus z q to the j. Okay. So if you write this, then the algebra becomes easier. So you can try this. But there is one important thing which I would like to mention about Sylvester's theorem, which is, I think, missed in the book, but it's a very well-known fact. So Sylvester's theorem actually implies Euler's pentagonal number theorem. You can already see that one side of the pentagonal number theorem you will get if you set z equal to -1. Okay, so if you set z equal to -1, this just becomes q infinity, which is one side of the pentagonal number theorem, and this z raised to the power minus j becomes the -1 raised to the power j, which you still need. Okay, so the only thing to take care of is how these things change. Okay, so if you set z equal to -1, then many factors of these things in the numerator and denominator will cancel out. I think only one factor will remain in the denominator, and that will cancel out with here, something here. Okay, so just take a look. So Sylvester's theorem implies Euler's pentagonal number theorem if you set z equal to -1. Okay, all right. So this brings an end to the preliminary things that we have been discussing so far. So do you have any questions? Because I think today was slightly different flavor. Before I go into the next part, which is the proof of the Rogers-Ramanujan identities. So let me stop for a few seconds.
This meeting is being recorded.
Okay, so so this brings an end to chapter 1 of the book. Okay, so I have not done everything from chapter 1, but basically this is end of chapter 1. Sometimes the flow is also different. So the author does something before, but I do it later on so that it's more natural in the progression. But basically, you are now set for chapter 1. So let's start with chapter 2, which is looking at. So there are a couple of things in chapter 2 which we will cover. So the first thing that we want to cover is Ramanujan's proof of the Rogers-Ramanujan identities. The next thing that I will go on is the combinatorial description of the Rogers-Ramanujan identities, which was given by Ishai Shur. And after that, we'll discuss a little bit of combinatorics, but then we'll come back and see a different style of proof technique for Q-series identities, which is basically Bayes' transform and Bayes' lemma. So that will give us not only Rogers-Ramanujan identities, but it will give us many other identities for free, essentially. Okay, so if we follow that technique. But first, let's do Ramanujan's proof of the Rogers-Ramanujan identities. Okay, so recall the two Rogers-Ramanujan identities were as follows. So let me write down the sum side first. So this was q raised to the n square by q cube n, and the other thing was almost similar, but you have a q raised to the n multiplied. Okay. So these were the two sum side of the Rogers-Ramanujan identities. I'm going to write down the product side, but I'm going to use Ramanujan's theta functions. Okay, so this is going to be equal to f of minus q square minus q cube divided by q infinity, and the second one is going to be equal to f of minus q raised to the power 4 q infinity. So if you want to see why this is true, what you can do is, actually we can do it. So if you remember f of so actually let's recall Jacobi's triple product identity because we are going to use it. Okay, so sorry. So f of AB was equal to minus AB infinity minus AB infinity and AB infinity. Okay, so this was Jacobi's triple product identity, and I'll only do the first one, and you will see why it's equivalent. Okay, so what is f of minus q square minus q cube in this case? So you will get q square q to the 5 infinity, q cube q to the 5 infinity, and you will get q5 infinity. Okay, now this is almost equal to q infinity. We're just missing two factors. Okay, so if you multiply q5, q square q5 infinity, q cube q5 infinity divided by q4 q sorry uh, multiplied by q4 q5, then you need to divide by the two new things that you have multiplied, so which is q5 and q4 q5 infinity. Now the top part just becomes q infinity, and the bottom you have q5 infinity, q4 q5 infinity. Okay, so if you recall Rogers-Ramanujan identities, in one identity you had, in the bottom you had 1 minus q raised to the power 5n plus 1 times 1 minus q raised to the power 5n plus 4. So if you write it in terms of the cube Oppenheimer symbol, that's just 1 over q5 infinity times 1 over q4 q5 infinity, which is basically the numerator that we have here. So if you divide f of minus q cube by q infinity, this goes away, this q infinity goes away, and you are just left with the bottom part, which is basically the product side of the Rogers-Ramanujan identity. Okay, and this is Jacobi triple product identity. Similarly, you can write down what this is. So I'll not do that, but you can write this down. Okay, right. So the proof that we are going to do would look very unnatural, because I'm not going to do so I'm not going to write down all of the steps in the basic arithmetic that we are going to do. Okay, so but I'll refer you to another Mathematica package which can do this automatically. Okay, so by now you must have you know experimented. If not, then I encourage you to experiment with the QGILE and FastGILE techniques that I showed you. Okay, so let's denote by say fz to be, so it's actually f of zq, and this is a two variable expression, okay, in z and q. But the interesting thing is that if you notice, if I set z equal to 1, then this is actually the left hand side of the first Rogers-Ramanujan identity. Okay, and if I set z equal to q, then this is the left hand side of the second Rogers-Ramanujan identity. All right, so fz is basically in some disguise giving us both the Rogers-Ramanujan identities. Okay, and let's set zz to be something like this. Okay, so it's m equal to, and this will look very complicated, but it's going to come out nicely in the end. And it should remind you of little bit of Sylvester's identity that we just saw, right? So it's very similar to Sylvester's identity. Okay, so this is our zz, and again, this is not only dependent on z, but it's also dependent on q. Okay, so zq. Again, if you think about this, so g of 1 and g of q, these are also going to be equal to f of minus q square minus q cube and f of minus q to the 4. Okay, so again, this is basically the right hand side of the Rogers-Ramanujan identities. Okay, so but I'll let you verify this on your own. Now the thing is, we want a recurrence for f of z and g of z. And if you can show that both of the recurrences are the same with the same initial values, then we would have proved what we want. Okay, so set, let's say, so the recurrence that we have is the following. So I'm going to write this down. Z of z is equal to 1 minus zq times z of zq plus zq 1 minus zq 1 minus zq square z of zq square. Okay, And if I denote hz to be zz divided by zqqq infinity, then this recurrence just becomes hz equal to h of zq plus zq times h of zqqq. Okay, so you can do this by hand, but there is a better way. Okay, and the better way is to use another package in Mathematica, which is called Q functions. So I'll not show this today, but I'll just give you the reference and the hint. Okay, so Q functions is a package which was again developed in RISC, from which we saw the previous packages, and this was done by Unsu and Eblinger, if I'm not wrong. Okay. And it's a new package. So the other packages that we saw were pretty old, so more than 20 years old. But this package is pretty new. So it's about 4 years, 3 or 4 years old. So what Q functions allow you to do, and the main motivation of Q functions, as far as I understand, is coming up from trying to generalize Rogers-Ramanujan type identities, okay, in more variables. So what Q functions allow you to do is that if you give as input your function zz, and then it's going to give you as output this one. Okay, it's going to give you this Q difference equation that we have, or the recurrence equation that we have. And if you give your input as hz, then it's just going to give you as output this recurrence for hz. Okay, so you don't need to do this by hand. If you want, you can use the computer to do it, and it's very routine now to do it. Okay, so I'll allow you to take a look at Q functions. It's just similar package, similar application, what we saw earlier. Okay. And if you use Q functions on F side, then you will get that Fz is also actually satisfying the same recurrence, which is f of zq plus zq f of zq squared. Okay? So this is square, by the way. I don't know why I did it. Then you see that now you have a recurrence for H, you have a recurrence for F, and both of these recurrences are the same recurrence. So if you're able to show that the initial values of F and H satisfy, then you are done basically. And that's what you can show, that F of 0 and H of 0 is equal to 1. And from there you can say that F of Z is equal to H of Z. Okay. So what you have proved is that F of Z is equal to H of Z, which was nothing but Z of Z divided by ZQ cubed infinity. Okay. And now if you set Z equal to 1 in this equation, then you get back the first Rogers-Ramanujan identity. And if you set Z equal to Q, then you get back the second Rogers-Ramanujan identity. So this was essentially Ramanujan's proof, but Ramanujan obviously did not have Mathematica. So he would have found these recurrences by hand, and including this. Okay, so it's not a very easy task, but of course you can, given the functions, you can find it, but to come up with the functions, it's a bit difficult. Okay, so this was, after all this preliminary, we were now able to see a very short proof of the Rogers-Ramanujan identities. But let me, go back to the steps and show you what things were involved. Okay, the first thing that was involved was Jacobi's triple product identity here. In looking at the product side. Okay, so while looking at the product side, you needed Jacobi's triple product identity. Next, you needed, Q functions, which was, you needed the Mathematica package Q functions. But now you would believe me that Q functions would work, because we have seen already 2 applications of such packages, FastXile and QXile. Okay, so in a similar way, you can implement Q functions. So those were the 2 things that were the main ingredient of the proof of the Rogers-Ramanujan identity. So that's just one proof. And as I mentioned, there are multiple proofs. We're going to see at least one more proof pretty soon. Okay. So again, this was probably fast, but if you go back, you should be able to appreciate what we did here. So the next part is going to be completely combinatorial, and I think it's probably a good idea to stop here today and do the next part in the next classes. But there is an announcement, which is that so let me stop the recording.